And if we have the standard model, in other words, no dynamics in the measurement equation, then the important transfer function for feedback controller design, G of S, is C transpose S I minus A inverse B e to the minus delay S. And GDI of S is exactly the same thing, replacing B, which is the column vector that multiplies U prime, by gamma I, which is the column vector that multiplies the I prime. So identical, except B is replaced by gamma. Okay? And given any G of S, we'll learn methods in this class by which we can do feedback controller design. So once we have G of S, we have done a lot of the work towards feedback controller design. Now, the way we got G of S and GDI of S is very good from a theory perspective. Can be nicely used if I have a very simple model, but it's totally out of the question for most real situations. I keep bringing up the unit obs lab column that we saw as an example, but even that is relatively small in some other real applications. Let's say we have an oil refinery with a 100-tray tower and 25 components. What would be the size of the A matrix then? Well, 100 trays
100 by 100.
roughly will have 100 stages. How many variables for each stage? We would have 24 mole fractions plus a holdup plus a temperature, so 26. So that's 2,600 state variables. So the size of the A matrix would be 2,600 by 2,600. So the number of partial derivatives you have to calculate just for the A matrix will be 2,600 squared. That's about 10 million. So clearly, this approach is not practical for most of the situations. But it lays the foundation for the approach that will be practical. Believe me, you cannot run a distillation column without feedback control. Okay? So that huge industry column will have a few control loops absolutely necessary for running it. And yes, we'll learn in the class how we can design those control loops. So we're going to go from here to the practical approach for getting G of S and GDI of S if we need. But before doing that, we need to gain some more understanding. And one question that you asked me last time, what can we do with that G of S and the GDIs of S? But one thing we can do is we can solve the model to find out what y prime of t, or equivalently y of t, would do in response to some changes in the inputs. And one thing I want to point out here again. This is an input-output model. X prime is nowhere to be seen here. For that 2,600 state variable model, this is still a scalar, and these are still scalars. Now, G of S will have a denominator that is a polynomial of degree 2,600. But it will still be a scale. So, clear? Just want to put the perspective of where we are and where we're going. So, today I will discuss, first of all, how given GU and GDI, we can calculate what y prime of t is doing. And for that, we're going to use two tools. First of all, the dictionary. And I'll just put two entries in the dictionary. Well, I guess three, but I don't have space for three, so I'll put the two most important ones. No, two is all I need. So, this has a lot of important subcases. Do you remember what's the Laplace transform of this? It's 1 over s plus a to the t. And the second one is the one that is pertinent to the time delay. F of t equals 0 for t less or equal to t. A delayed function for t, well, less than. Doesn't matter because the two meet at t equals d. And that is h bar of s e to the minus st, yes. And what is h bar of s? The Laplace transform of h of t, not of h of t minus t. Okay? Of the undelayed h. So that's one tool we will need, and the other tool we will need is partial fractions expansion. And you've learned a method to do that in DFQ, and I believe in DFQ you're learning the technique of matching coefficients. This is a correct and fine method, but I have a much more practical and easy to use method that we're going to learn in this class. All right. So, what can we do with G, U of S and GDI? So, first of all, I want to emphasize this is true no matter what each disturbance and the manipulated input is doing. Okay? So, transfer functions don't depend on what each input is doing. Why? The output very much depends on that, but not the transfer function. So, to be able, so one answer, okay, answer one, predict system response. To changes in the inputs. And answer two, I put in the bottom because that doesn't come immediately. Design controls. So that's for link. Answer one has really three steps. Two steps would work, but since we're getting something up with three steps. And we'll do an example of that, a couple of examples of that today, and we'll also talk about partial fractions expansion today. So step one, from whatever the input is doing and the disturbances are doing, obtain, using dictionary, have gotten a little bit better. You can read them, right? Well, yeah. Are you okay with my ampersands? Union? Once we have this, so I almost put parentheses here because that's obviously trivial. And step 3, DFE stands for Gaussian Harmonic expansion, and y of t, of course, the actual measured output is going to be the nominal value plus the deviation. So that's one thing we can do. We can utilize these steps to find out what's the output of the system, and then we can plot that if we want. Okay.
Oh, what is that? Y of t?
What is y prime of t?
Yeah. The
It's-
last equation you wrote, what is that?
Well, that's that the actual measured output is the
Oh,
nominal
okay,
steady
yeah,
state plus the deviation. And we get the deviation from inverting using Russell fraction expansion in the dictionary. From here, we get y prime of t.
Okay, never mind.
So once we get y prime of t, we actually have the actual y.
Okay.
That's,
Yeah, I thought it had like a name. Specific name. No, it doesn't.
that's the actual measure. Clear? Any questions? So we understand where we're heading, hopefully.
Wait, that's the measurement equation?
No, that's what the actual measurement is.
Oh, okay, okay.
So for example, suppose that a disturbance changed from, let's say, nominal steady state 3 to a new value 4. Okay? So let's say di changed from 3 to 4. Okay? I want to find out what happens to the measurement. What would happen, let's say, the temperature of the coolant increased. Okay, if it's temperature. Okay, let's say the flow rate of the feed of the reactor increased from 3 to 4. Okay? And I'm measuring the temperature there.
Okay.
How will the temperature of the reactor respond? So the temperature measurement at y is temperature measurement. And let's say at 9:30 a.m. this change happens. Okay? What this will be able to tell me is that here is your temperature measurement. At the beginning it may have been 300 Kelvin. Here is 9:30 a.m. And what happens is, in this case, first it stays flat for a little bit of time because it takes time for the change to portray what happens to the temperature measurement. And the feed flow rate first caused the temperature to start going down, but then after a while the temperature will go back up, and let's say ultimately the temperature ends at 310 Kelvin. So we'll be able to get this picture of what happens to the temperature measurement given this change in the flow rate of the feed of the reactor. Clear? So that y of t, you can translate it into this picture.
Okay.
Clear?
Yeah. Sort of.
Everybody okay? Right. So let's now use a very simple example. So for a very simple example, we had the model this was concentration in the reactor is minus 0.111 x prime plus 0.0018 u prime plus 0.0111 b prime, and y prime at t was x prime at d1 prime in this case. Did I use x or x1? I think I used x1, right? Can you look at your notes? Did I use x or x1? So last time when I had this. I think x1. Can you verify? Just want to be consistent from the previous. Sometimes I use, in this case, x is the entire vector. I use x1?
Yes.
Okay. Let's put it 1. And I know I use u1. So x1, right? So in this case, the A matrix is simply minus 0.111. The B vector is 0.0018. The gamma matrix, which is also the first vector and only vector, is the scalar 0.011. And C transpose is simply 1. So these are the parameters that we have in the model. And if we use the above equations for GG and GDI, we would find GG of S is C transpose 1 times the inverse. What's the size of the A matrix? 1 by 1. What's the identity? 1 by 1 size identity.
1.
That's the one time when you're correct to say 1 for identity. Okay? Every other time it's an S. So S times 1 minus the A matrix is minus 0.111. Inverse. B vector is 0.0018. E to the minus 5s. And as strange as it is, it actually happened to a student many years ago, and she was a good student. I think she ended up with a B plus in the class. But she got totally stumped in an exam in the inverse of this matrix I have in the bracket. What's the inverse of the matrix I have in the bracket?
Inverse?
Oh, of that matrix I have in the bracket. Okay. So that's
It's the 1? Or?
1. This bracket is S times 1 minus minus makes plus S plus 0.111 inverse 0.0018 e to the minus 5s. What's the inverse of the matrix that I have in the bracket?